The transition to next-generation energy storage and green hydrogen faces a severe bottleneck. The industry relies heavily on rigid, expensive, and scarce precious metals like iridium and platinum, creating a heavy, sluggish system that is difficult to scale. To bypass this limitation, material scientists are turning to two-dimensional nanomaterials, specifically a class of compounds known as transition metal dichalcogenides, or TMDs. Building a functional component from these materials requires a precise four-step engineering process: selecting the base material, performing hydrothermal synthesis, activating the atoms, and executing a mass manufacturing scale-up. Mastering this sequence allows us to take a fragile laboratory curiosity and engineer it into an industrial-grade component, reducing our dependency on expensive precious metals to a fraction of current industrial standards. Step 1 is selecting the right base material. Currently, molybdenum disulfide, MOS2, serves as the industry standard for two-dimensional materials research. However, MOS2 has a critical flaw. Under intense charge-discharge cycles for advanced batteries, it suffers severe structural instability. The chemical structure breaks down. MOS2 disintegrates into polysulfide species and molybdenum nanoparticles, resulting in rapid capacity fade. We solve this by substituting a superior alternative, Tungsten Diselenide, or WSe₂. This material features a highly stable XMX atomic architecture, sandwiching a plane of tungsten atoms perfectly between two planes of selenium. Under intense electrochemical stress, this specific structural arrangement allows the WSe₂ to maintain its metallic phase and provide continuous electrical conductivity without disintegrating. Selecting WSe₂ over MOS2 provides the required foundation to build an electrode that survives the high-voltage demands of lithium-air and other high-capacity systems. With the base material selected, we move to Step 2, structural synthesis. Simply stacking flat sheets of WSe₂ on top of each other physically restricts the flow of ions, severely limiting overall battery capacity. We have to change the macrostructure. We do this using a hydrothermal method, placing the WSe₂ into a liquid solution and subjecting it to extreme heat and high pressure. Inside this reactor, we introduce specific chemical additives: graphene to improve conductivity, iron oxide, and a conductive polymer called polyaniline. The extreme pressure forces these flat layers to peel apart, warp, and lock together with the additives. This forms a porous 3D network, increasing surface area for ion transport, pushing output to 401 farads per gram. The hydrothermal process physically upgrades the material from a restrictive, slow pathway into a high-capacity superhighway, capable of retaining 89.3% of its charge over 5,000 cycles. Now we have a highly porous 3D structure, but the flat surface, or the basal plane of WSe₂, remains chemically dormant. Step 3 activates the surface through a process called atomic-scale vacancy engineering. The first phase of this strategy involves doping the material by substituting trace amounts of platinum directly into the WSe₂ crystalline layers. This chart of defect formation energies confirms the viability of ripping out selenium atoms to create physical vacancies. At the neutral charge state, removing selenium leaves unsaturated tungsten coordination sites that act as powerful, highly active catalytic hotspots. These missing atom gaps violently attract passing oxygen and water molecules. The kinetic interaction at the hotspot rips the chemical bonds apart, forming the oxide intermediates that facilitate the reduction and evolution reactions required to generate hydrogen fuel or store energy in a battery. Engineering these atomic defects allows our ultra-thin sheets to achieve a 38% higher hydrogen production rate compared to standard commercial benchmarks. By deliberately breaking the material's perfect structure, we achieve high hydrogen yields while using 65% less precious metal overall, making green hydrogen economically viable. Step 4 addresses the scale-up trap. A highly active catalyst built in a laboratory beaker often fails when we attempt to mass produce it. Traditional synthesis methods, like chemical vapor deposition, require massive energy inputs, extreme heat furnaces, and expensive vacuum environments. These harsh conditions scale poorly and risk destroying the delicate 2D structure we just built. Furthermore, mass production often triggers agglomeration. 2D materials tend to clump together into useless, dense, granular particles, effectively destroying the active surface area we engineered. To bypass the need for vapor deposition and intense heat, researchers at the Korea Institute of Science and Technology and the Institute for Advanced Engineering developed a room temperature stirring method. By processing the materials using standard industrial shear exfoliation mixing, both the platinum substitution and the selenium vacancy formation occur spontaneously under ambient conditions. Operating at room temperature preserves the structural integrity of the material. It actively prevents agglomeration, ensuring the nanosheets remain laterally extended with their active surface area fully exposed. Eliminating high-heat vacuum furnaces in favor of scalable, room temperature mixing allows us to transition this technology out of scientific isolation and into a mass-manufactured commercial product. The engineering pipeline is complete, selecting stable WSe₂, synthesizing a porous 3D structure, engineering catalytic atomic vacancies, and scaling production via room temperature stirring. The physical result of this four-step process is an ultra-thin, paper-like electrode. It is highly active, mechanically stable, and ready for deployment. This specific component is optimized to operate inside the architecture of next-generation lithium-air batteries, or to serve as the anode in high-efficiency green hydrogen electrolyzers. For the exact chemical ratios and the original research papers detailing the room temperature stirring method, check the links in the video description below. By combining precision atomic-level materials engineering with scalable manufacturing techniques, we can cut our reliance on scarce precious metals and build the physical components required to power a sustainable energy grid.